Spent a little bit of time reviewing. You guys, again, I mentioned this yesterday, had a lot of extra time even yesterday to work on it, on review stuff. So I kind of want to open the floor to questions first, like I try to with all reviews. Questions, whether they're from the problem set, whether they're general questions, whether they're questions about formatting, whatever it may be. So I'd rather start by opening up the floor with that, and then I can go into specifics if we need to. Okay?
Go over the steps for the calculator.
Sure. I'll tell you verbally. I'm not going to do it again on the computer, but I can tell you what to do.
Yeah.
If you want to write it down, it might be useful. So you're talking about solving a quadratic, right?
Yeah.
All right. So the first step is to get your equation equal to 0. It's got to equal 0, the equation. So set equation equal to 0. You move stuff around in the equation, you need equal to 0. This is solving using the quadratic formula, but on the calculator instead. The second step is to go to y equals. Key on your calculator that says y equals. Input the equation you have, or wherever you have t, put in that x key. Okay. The third step is to press, I would personally zoom in the proper way, so I would probably press zoom 6 next.
All right.
I would press zoom 6 next. That'll give me a negative 10 to 10 graph and a negative 10 to 10 graph. Now, if the time is more than 10 seconds, you have to zoom out. Because you're new to this, most likely the time will be in between that region of 0 to 10 seconds. Okay? The following step would be to press second and then trace, which will bring up the calculate menu. Again, second trace. It'll bring up the calculate menu. You're going to choose the option that says the word 0. It's option number 2. It says the word 0 because you're finding the zeros of the function. Then it's going to say left bound, question mark. The calculator will say to you left bound, question mark. And all you have to do is type a number to the left of your root, the root that you're looking for, the x-intercept root. Type a number to the left of that x-intercept, hit enter. Then it will say right bound, question mark. Type a number to the right of that x-intercept, press enter. And then finally, it'll say yes, question mark, just press enter. What's important to recognize, what's important to recognize here when you're taking these steps is that if you have, say, a graph that looks like this, okay, when it asks you for the left bound, if you're trying to find the root on the right, when you give a left bound, you have to pick a number somewhere in here. You cannot go to the left of the other root. So by picking a number somewhere in there, remember what it does, it puts up a wall. So let's say we choose this value here, it puts up a wall. Then it'll say right bound. As long as you pick a number to the right of this without going off the graph, you're good. It'll put up another wall. And then when it says guess, question mark, it will automatically search in this region, eventually finding your root. Physically what the calculator is doing.
So you can't find both of the x-intercepts if you go outside of.
Correct. If you do, it'll give you one of them, but it'll be arbitrary. It might always give you this one. And what if you need this one, right?
Okay.
So if you put the boundaries out here, you just don't know which one it'll give you. You can do that and it'll work, but you'll always get the same root over and over again when you need the other root also.
Wait, so can this work if I look at these 2 points for left bound and these 2 points for right bound?
So this would be the left bound of this root. This would be the right bound of this root.
I don't understand.
It's a wall. So here's your root. Put a wall to the left
Yeah.
and put a wall to the right. So these are your left and right bounds for this root. This is your left bound and this is your right bound for this.
Okay.
So always look at the root itself and just go a little bit to the side of each. Okay? Yeah? Practice it, okay? And if you're not really sure still, there's a video up on this videos from class that some YouTube guy just literally recorded himself doing it. He doesn't type in the number directly for left and right now. He uses the trace command, which is fine. But I find it much faster when you literally just type in the number. It saves you 10 seconds at least. All right. Questions? Elias, go ahead.
Yesterday, near the end of the lesson, I forgot exactly what it was, but it was after we found the answer, you were like, say we multiply this by like a number.
Oh, I said, what if we change the height from 20 to 25 or something like that, right? How does it change the answer? And all I wanted you to see was that in the equation, say this was the equation here, it just changes one part of the equation. So say suddenly the cliff goes from 20 to being 25, you would only have to change that number.
Okay.
That's all it was.
That's it?
Yeah, I was just saying if you vary one of your parameters, how does it affect your answer? And you'd have to change that one parameter in the work and then recalculate your answer. You don't have to redo the whole problem, knows what I'm saying, right?
Okay.
So if you're given a part that says, determine the impact speed if the height of the cliff is 20 meters, if it's 25 meters, if it's 30 meters, the impact speed should get greater and greater because you're launching from higher and higher. So when it hits the ground, it'll be faster. But you don't have to do the problem 3 times. You just recalculate it by changing y every time.
Okay.
Yep, good question. What else? Let's write our 3 formulas down. We have 3 new ones from this chapter, right? Oops, it's really x, not y, but let's recognize that it could also be y. And I think in this class, if I recall correctly, tell me if it's right. I think I already went over like things like what happens if it's a free fall? What happens to all the equations? Right? I talked about that already? Like how do the equations all vary if suddenly it's a free fall? Did I or did I not? Be honest, that's fine. Okay, so that's fine. So let me go over that. So I posed the question, it must have been the other section. I posed the question, what happens to your equations when an object is undergoing free fall where it's physically dropped like that? How does it make these equations change and in what way?
Initial velocity.
Correct. So every one of these equations would go like this. Right? All of those parts would drop off. And it makes your equations a lot simpler. So the minute you have a free fall problem where it's being dropped, or remember this problem? We did this yesterday. When an object is launched and then it's on the way back down, if you're physically only looking at the way back down, that's a free fall, really. Because when it gets to the top of its path, what do we say? It does. It stops. So it's as if you're doing this and holding it at the top of the path and then letting it go. And it's free fall. Okay? And it's a free fall. So that makes the equations much simpler. VI's all drop off. Yeah? What if we're looking at a problem only on the way up? What simplification can I make to all my formulas, or 2 of my formulas? If it's only on the way up. Well done, Kev. VF becomes 0 in that case. VF would go to 0. Okay? Again, VI would have a value now, though, because you're launching it from the ground. So here we go. Let's look at the problem. This object is launched from the ground with some initial velocity. It's on the way up, and we're trying to find max height. Well, if we're only concerned about the way up, we can set VF equal to 0 for all of those problems. Anytime you're only on the way up, VF equals 0. If it's only on the way down or being dropped, VI equals 0. Okay, it's not a coincidence that it works in both these cases. We talked about truncating or breaking the problem into pieces and how the end of the first part is the beginning of the second part. I talked specifically about in the other section. I gave an example. I was asking them who runs cross country, and I think Bridge and Danny Gramberger did, so we used them as volunteers. And what I said was, how would you hand off a baton in a relay race? And how would you do it? Would I be waiting here? You run cross country, so would I wait here for Elias to run into me and then just take the baton and run with it? What would I do, Elias?
Start running as
I would run like this, right? With my hand out, wait for the handoff, wait for the handoff, and then I feel the baton in my hand, I grab it and run. So the velocity that Elias has at the end of his part of the race is equal to the velocity that I have at the beginning of the race. Think about it. I'll draw a picture again. So I gave the example of this the other day, and I'll show you an animation of it. So Elias is running. Okay? And here I am waiting for him to hand off the baton. As he's running, let's say, at the end of every leg of the race, you should be going as fast as you can. Now, obviously, in a relay, you have to be careful at the same time, though. It's not like you're sprinting to a finish line. So Elias is at top speed. He's reached his top velocity. He's running at like, I don't know, let's say 15 meters per second. Very high velocity. He's running at 15 meters per second at this point right here. And we would call that his final velocity, right? Well, as soon as he hands off the baton, I have to be moving at the same speed for it to be a nice handoff. So my initial velocity has to be equal to his final velocity for there to be a smooth transition in the relay race. It's very similar to problems that we have done, where we break a problem into parts. So let's say, for example, we did this already once with the problem set question about the girl playing baseball, sliding into the base. So again, let's do one. Let's think of a car. I have not talked about the car with you guys, right? No? Let's do one with a car. I can't draw well, so. There's our car. Okay, there's the door. So the car is going to the right, and this car is moving at a constant velocity the entire time. So we'll say it has a constant velocity it's moving with. And then suddenly, as the car is driving, let's say it hits like a patch of dirt, or goes off the road into a patch of dirt where there's a lot of stuff on the ground. Well, what would dirt do to the car? Yeah, it would most likely create more friction. The car tires can grip it, but it will probably slip a little bit in the dirt. So in general, we'd say it would slow it down. So what we could say is that the velocity of the car when it reaches the dirt is this V bar value. And if it's 6 meters per second, or that would be too little, 60 meters per second, that means that when the car reaches right here, the initial velocity of this problem is 60 meters per second. And if the dirt is accelerating it in the negative direction, also known as decelerating, slowing it down, we can automatically conclude that VF will be something less than 60. And you see how that works? If I'm undergoing deceleration, my velocity must decrease, or it must get smaller in magnitude, I should say. So if I get an answer of VF equals 90, probably doesn't make much sense. That means that you give it a positive acceleration. When in reality, we're talking about here, in this context of this problem, we are talking about a negative acceleration in this context of this problem. So breaking the problem into pieces is very, very useful. If I give you parts A, B, and C, like I've mentioned, it's possible I'm having you break it into pieces. I ask for the max height, then maybe I ask for the impact velocity. So part A, it's on the way up, and part B, it's on the way down. Right? So it's possible that the part A, B, and C are asked in a certain way on purpose, so that you do them in that order. If you can't get an answer for part A, but it affects part B, what do you do? What do you do? You don't want to get double jeopardized, right? What do you do, Elias? What do you think?
So we can pick a number.
Yeah. Pick a number for your answer for part A. It's going to be wrong. You're not going to get credit for A, but at least you can use your answer for A in part B. Right? Because again, if part B has to use the time, and part A has you calculating the time, you can't do part B without having the answer for part A. So if you don't get the answer for time, you know what? Eat the hit. Take the 2-point loss for part A. But write a statement that says, let time equal 2 seconds. Make up an answer. It's wrong, but make it up. And then use 2 seconds in part B so that you can maybe calculate the distance traveled in part B, or the impact velocity in part B. But if you can't get part A, don't just assume you're not going to do part B. That's double jeopardizing yourself, meaning A affects B, so you get losing points for both. So pick an answer for A and utilize it in B. Other questions? Other questions? How do we feel about graphs? How do we feel about graphs? Want to do an example together? I think it'd be a worthwhile one to look at. All right. Let's say I've got the following. Let's say it's a position time graph. Okay? And here's the path of the motion. I'm not going to give numbers, okay? I'm just going to give paths. So let's say it starts at some initial position. We don't know the number. It starts to increase in position. It remains in the same position. it decreases dramatically in position, and then it increases at a higher rate in position. First, tell me, what could you give me as a description of motion? Actually, that's too easy. What could the velocity graph, or what would the velocity graph look like for this scenario? What would the velocity graph look like? And I want you to do it in pieces. And when you answer questions like this, I highly recommend that you draw the velocity graph directly below it so that you can reference the same location. So this is an important part. That's an important part. That's important right there. So what I'm doing is I'm putting little tick marks wherever there's some sort of a change in position, right? And there's a dramatic change. So for the first part of this trick right here, what can you tell me about the velocity? Based on the position graph of this, what can you tell me about the velocity? The velocity is constant. That's one thing you can tell me. Give me a second thing you can tell me.
Velocity is positive.
The velocity is positive. And that's really all we know. Again, how do I know velocity? Velocity is the slope of this. So since that slope is constant, as Nick said, and positive, as Brandon said, I know that it's going to look like this. I don't know what the height is, but I know it should be a constant line for velocity, and it should absolutely be positive. It should be positive. Okay, that's section 1, part A. The second section, what can you tell me? Kim?
Velocity is 0.
Velocity is 0. Very good. How come, Kim?
Because the position is the same.
Correct. The position here is constant, or it's not changing, or what's the slope of a horizontal line? 0. So any of those ways you want to interpret it and justify is fine. If it's a short answer, you need to justify. If it's a multiple choice, you need to be able to do this and just get to the answer, right? Justification doesn't matter as much there. And technically, I should connect those. It's a quick, steep change, just like this, right? This is what's happening. It's physically what just happened there, right? I abruptly stopped, so my velocity went from being all positive to 0 velocity. And again, why is it 0 velocity? Because at the end, my position did not go up or down. Here it goes up, here it comes down. Right?
That line that's connecting the two parts shouldn't be straight, right?
Technically, it shouldn't be a vertical line. There should be a little bit of slope to it, because what do I have to do to stop? Slow down. So you should see a decrease in the velocity. It's just a really, really steep decrease, right? I'll follow up with other questions in a minute. Let's go to the third part. There's a follow-up. We can talk about that. Joe?
It's constant and it's negative.
Yeah. And Joe, relatively speaking, should it be at the same height as this one? Should it be here? Should it be further out?
Further down.
Why?
Because it's on 0 on the x on the position time graph, and the first point is kind of like it's a lot higher than that point, so that point will go a lot lower compared to where the first part is on the velocity time graph.
So Joe's picking up on the fact, I'm going to simplify what we're saying, that this position change was only a little bit over a long time. This was a lot of position change in a short time, which means in the second case, yes, it's a negative velocity, but the line is much steeper, much steeper. So this graph at the bottom here now should be a little bit lower, at least somewhat lower than the other one was, like that there. Okay, so maybe this velocity is positive 2, this velocity would be like negative 6. The magnitude, the number is definitely bigger because it's steeper on the way down there. And then finally the last part. This is the one that we've kind of alluded to in the lab, we haven't got into it yet. Kim, what do you think?
So like since the position the position is set constantly changing for that one, would the velocity be like a diagonal?
What do you mean by diagonal?
Because like if it's accelerating and they're not constant, and the velocity is not also constant.
Correct. So what kind of a diagonal line should it be?
Positive.
Very good. An increasing diagonal line. So Kim is saying this should look like this here. And let's discuss that. That's the one that's probably the toughest. So look at the position graph. In the position graph, it looks like in this little time period, the person barely moved. Then in the same time period, they moved a lot. Then in the same time period, they moved a real lot. So this graph right here, okay, that I'm pointing to, can be demonstrated like this. Small, bigger, 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 bigger steps, which shows an increase in my velocity, and that's this right here. Went from zero velocity, or sorry, not zero, but went from stopping for a quick second here. Remember, position was decreasing, then position increased. I have to stop to do that. So it stopped for an instant and then increased velocity. Anytime your position graph goes from being a decreasing to an increasing, you have to stop. Right? Because this path was this. It was me walking this way. And then suddenly, it's this. Pretty much faster. So I had to stop at some point. That's this little zero velocity right here. Okay? Now, one more follow-up for you. What can you tell me about the acceleration of this object in each region? Acceleration now. We've done position, we've done velocity. I don't want you to graph it. You can graph it, it's not that hard to. I want you to speak about what's happening here. So what's happening in this region first? Why not? Yeah. Think about the velocity graph. The velocity is constant, isn't it? The slope of this line is? That one's positive. The slope of this line is 0. So there is 0 acceleration. 0 acceleration. Here? It's not moving. It's 0 acceleration and 0 velocity, both. Here it's got a negative velocity, right? But still 0 acceleration. Again, remember constant velocity, which is 0 acceleration, not moving, 0 acceleration, constant negative velocity, that's also 0 acceleration. Whenever you hear the word constant velocity, you know that it's 0 acceleration. How is this last region right here? What kind of acceleration? Positive. The slope of this line is positive, so you know acceleration is positive. So let's write down our two facts that are really important. Slope of position versus time is velocity. And then down here, slope of velocity versus time is acceleration. You will absolutely 100% have to interpret graphs. Whether it comes up as multiple choice and I ask you questions about different regions. I might say to you, it's multiple choice. What's happening to the object's velocity in region 3? Well, the object's velocity is negative and it's constant in region 3. Region 2, region 1, region 4. And they'll be labeled accordingly on the graph. Okay, or maybe I give you a scenario and I tell you a story and write a paragraph. You read that paragraph and I say, now show me a graph that dictates this motion that I've described in the paragraph. Remember your lab, those kind of questions you had in your lab there? Those are good examples of that. I didn't give you your labs back yet because I've been waiting on people to hand them in still. 2 people were late. What I will do though is I'll put a blank copy of the lab up on Moodle this weekend. So if you want to look over it again to get an idea for studying for reference, it might be useful. Okay, so I'll put a blank copy up in your documents and handouts of that lab so you guys can at least see it, so you can see the kind of questions you could expect. The lab questions are great examples for graphical stuff.
Yeah, I think question, you're saying like region 1, like you're talking about that flat line, but what about the lines that are vertical?
Yeah, I'm not even referring to those because if I go back up to my position graph, I only care about these 4 regions in the position graph. Like that. What I'll do on the test is either use letters or numbers, and I might even use letters at like each increment. So I might say like this, Brendan, I might say this is A, that's B, C, D. So I might say from A to B, what's happening? From B to C, what's happening? Or I might say from time equals 0 to time equals 2. Or time equals 2 to time equals 5, if there were numbers given. It'll be very clear as to what it is, but it can be given any way it is. And it's able to interpret graphs. Okay? Good on graphs for that? Yeah? All right. Hey, so yesterday we did a lot with free falls, with vertical motion, right? But let's not forget that we started this chapter off with horizontal motion. Accelerated horizontal motion. We started with the 3 formulas, x equals VIT plus 1/2 AT squared. VF squared equals VI squared plus 2AX. Remember, everything was in terms of x. So So we can't forget for this test that it's also horizontal motion. So let's look at an example of that and get an idea of how we, can continue to utilize the knowledge we've already gained from the past stuff or from the free fall stuff. So let's say an object changes velocity from 20 meters per second to 12 meters per second. An object changes velocity from 20 meters per second to 12 meters per second in 5 seconds. Determine the object's displacement. An object changes velocity from 20 meters per second to 12 meters per second in 5 seconds. Determine the object's displacement. So it started at what velocity? That's my initial. It ended at? How long? So my givens are already there for me. Spelled right out for me. What's the problem with this problem? What's the problem with this problem? Elias?
We only have 3 of the variables, and for the equation to be acceleration.
Yes, for all 3 of our equations in this chapter, you need the acceleration of an object. So if I give you a problem on the test that does not give you the acceleration outright, the acceleration is, the object is decelerating at, if I don't give you the acceleration, you have to start by finding it first. So it might not be a part A, B, C for a problem that it just asks you for displacement, but technically part A is find the acceleration. Then part B is find the displacement. So there are 2 parts of this problem even though they're disguised. Okay, so again, if I want to use formulas for displacement, I can try both. And I can look at both and recognize that I'm missing acceleration there, or even using this formula, I'm also missing acceleration there. So either one of these formulas will work in this problem, but only if I have acceleration. Okay? Now, fun fact, check this out, this part you might like. You might like this thing, ready? Take this equation right here, and instead of figuring out the acceleration, just put the formula for acceleration in for A. What's the formula for acceleration? It's the first one.
VF minus VI over T.
Very good. Final velocity minus initial velocity all over time. You can just replace A with that expression. And then you don't have to actually find A inherently. You can plug it right into your formula. So again, you could start this problem by solving for A, VF minus VI all over T. That's one option. Or you can approach this problem by substituting in for the expression for A. And I'll plug it in red so you can see it clearly. Like that. That's also another way to approach this problem. So you could take the numbers, VF, VI, T, and get a value for A. You'll get a number, and that's fine. And then you can directly plug that number in and solve. Or, showing you the other approach on the right, you can replace A with its equivalent expression, which is up top, using what method am I using to do this? In the summer you did this with systems of equations. What method do you use to solve? Substitution method. That's why I had you do it in the summer. It's not a coincidence that these things are coming up that you practice. Substitution method, you take an expression and substitute it for its equivalent variable, which in this case is A. And then we can plug in everything we know. Okay, 20 times 5 plus 1/2. This is 12 minus 20 all over 5 times 5 squared. If you notice and you're good at your algebra, you could also cancel this t with one of these t's also, right? Did we see that here? There's a t in the denominator here, and there's a t squared over here. These could reduce and leave just the t up here. Because you have 5 and 5 squared, it's like 25 divided by 5. It's just 5 anyway, right? So I can just cross cancel one of these 5s, and it leaves behind a 5 up top like that. Or I can cancel this t with one of these t's and enough of that. So you can do it also, make it simple on yourself. I'm indifferent. You can do it either way. I happen to be an algebra person, so I would absolutely cancel it, but I don't want to mislead or confuse anyone, so I'm not necessarily doing that. But again, cancel with one of those t's that are up top. And you'll get some sort of a number for x here. Okay, you'll get a number for x here. What other types of problems? Yeah, Kim, go ahead.
Why don't you use the other equation to get the acceleration?
Because I recognize that I never asked you in this problem for acceleration, right?
Yeah.
So it's just an intermediate step. So if I can get rid of that step, Kim, and not actually calculate it and then plug a number in, I can just use the formula and plug it right in. If part A of the problem said, find the acceleration, and part B said, find the displacement, then you definitely need to get the number first for acceleration, and then do the displacement. But instead of getting a number for acceleration, I just plug the formula for acceleration in for acceleration. Either way works. Either way is fine.
Yeah, so can you cancel the off?
Yeah, absolutely. One of them. So I would cancel this with one of these t's, which would leave you with just a 5 like that. Yep. And I would do that. I felt like I was making this a tough problem already, and I didn't want to confuse anyone with that statement. So that would cancel with the squared term. The 5 drops away, and that squared term is gone. Yep, absolutely. We still have time. We still have 5 minutes. I'd like to ask if there's any other questions that you want to ask about. Any things that you were confused about, whether it was in the problem set. I will definitely post the solution of the problem set. I'm only waiting on one student for their work, and it is due by tomorrow. If they don't turn it in by tomorrow, it's a 0. So I'm waiting on one student at this point. Nobody in this class, don't worry. You would know that obviously because you all turned it in. But I will definitely post the solution at the latest tomorrow night at like 8 o'clock or before the evening hits around, because that's when it's technically due for that person. But I'm hoping to get their work in today, and once I get it in, I'll make the solution available on Moodle under problem sets. It'll say problem set 2 solution. I'm not going to tell you what it is.
Who is it?
You go like question
Who is it?
Oh, no, they know they're missing it. They just have to finish with like one problem and then upload it. So it'll definitely be turned in. Anything else I want to go over here? We had so much time to review. That's why I'm thinking like out of yesterday and today already. Remember, obviously, that all 3 formulas work with the variable y for vertical motion. I'm just looking at your text at different pictures so I can get an idea if I have anything that I want to discuss as we go through it. I would say that the focus of your test mathematically would be out of section 3-4. If you're wondering like numbers-wise percentage. For mathematical parts, you probably have 3 to 5 problems for the math part. You'll probably have like 3, maybe 4 short answers, and then about probably 5 to 10 multiple choice. But of the math problems, out of those 3 to 5, it'll probably only be like 1, maybe 2 questions from 3-1, 3-2. And then the rest will be 3-4, where it's vertical motion. Because I can ask you a lot more with vertical motion problems than I can with horizontal motion. Okay, because vertical motion we have up and down. Horizontal, I mean, it's right and left for sure, but it's not the same where you have a force pushing you back, besides air resistance, which we're considering negligible. Free fall, make sure VI is 0. Totally up to you. I mean, they give you at the end on like page 111. They always give multiple choice questions in the textbook at the end of the chapter. So this one happens to be on page 111. You could absolutely just do those problems as practice. That's a good way to look at it. But there's no real right or wrong answer to that. Another thing you could do, you could definitely do this if you want to. It's up to you to decide. I use all the questions from Regents exams. I do. I'll be honest. You usually are aware of that. The Regents exam in New York is all multiple choice. And all of their physics exams are up online. If you just type in New York State Regents exam physics, you can view them all for the last 20 years. So what I do is I go through some of them, and based on the topic of the test, this happens to be kinematics or one-dimensional motion, either of those phrases, kinematics or one-dimensional motion. Those are the type of questions that are appearing on this. So you can look through the multiple choice real quick at the problems. It'll be toward the beginning of the test, because it's the beginning of the topic in the Regents exam. Or you can honestly just Google one-dimensional accelerated motion multiple choice questions. And I guarantee you'll find tons of Google results for multiple choice problems. Good question. You should always practice multiple choice. Yeah. I think it's useful to practice multiple choice always. No, you can't obviously. And some of mine come from like the 1970 exam, so you're not going to literally do all of them, but those are good sample examples for you guys to work with. I just happen to look through them over the years. All right, you guys can go. Go ahead.